now we will hear from Frank Schroeder. Frank's been using Go since 2011. Frank, is that about right? And he's now a principal engineer at Northvolt, which who make obviously green batteries in their many gigafactories around Europe. And Frank's going to talk to us about how he's been using Go to help build those batteries. Over to you, Frank.
Thank you. So I need to, I have probably a bit raspy voice today. Let's see that it lasts. Let's hope that it lasts. Let's see whether I can manage the technology here. So let's start with this and then. Okay. Is the sound okay? And can everybody hear my voice? My somewhat squeaky voice. Can you see the screen? Okay, good. So thank you everybody, and thanks for having me. Thanks Martin for inviting me to give this talk. So this is a talk where I'm going to show you what we are doing with Go in manufacturing for a battery company that I've been working now for 2.5 years, and it's more on a presentation about the usage of Go. So I think I have one slide with a code example, but it's more about the journey on what is actually possible with Go in this environment. So I want to start out with let's see if I can do this here. Yeah. So Go is an so we're using Go in somewhat unusual places and as a somewhat unusual choice in manufacturing, because there aren't really a whole lot of companies. And when I ask, the only one name comes up. It's Tesla that's using Go in manufacturing. And sorry, and we're using Go mostly because so I was one of the first engineers that got hired, and I'm really fond of Go and its simplicity and the language itself. And so we started to see how far we can push this. And so today I want to show you what we've done a little bit. Let me start by telling you a little bit about me, because I'm not a regular on the Belfast meetup. So you've probably seen my name, or you may have seen my name as Magic on Air somewhere on the web. I'm married. I have 2 kids, 6 and 8, who are hopefully sitting downstairs quiet for the next hour. I'm a software engineer. I've worked at Netscape back in the days when they're relevant. I worked at eBay in Amsterdam and for a brief while at HashiCorp. I'm using Go since 2011, and then we were using Go at eBay in Amsterdam as probably the largest production team in the Netherlands. That's also where I met Martin, trying to find more Go people when there weren't any Go people. So I have a couple of what? I am sharing presenters view. Okay, then I'm sharing. I'm not sharing the. Oh, let's try this one. This is better. Can you now see the real slides? So who's Northvolt? So Northvolt is a battery manufacturer in Sweden, and what our mission is to build the world's greenest battery. And what that means is that battery production requires a lot of energy because there's a lot of moisture that needs to be evaporated. So in general, you need a lot of energy for the initial process. And then in north of Sweden, we have a bunch of hydropower that we can use. So we can use 100% renewable energy for this energy intensive part. The company itself was founded in 2016 by Peter Caso and Paolo Cerutti. We're both coming from Tesla, where they were building and responsible for supply chains there. At present, we have, I think, 940 employees from 71 countries. So this number is a bit old. And we're currently building a gigafactory in Skellefteå, which is in the Arctic Circle. We have a test factory in Västerås, which is also in Sweden, which is about 150 kilometers from Stockholm, where I currently live. And we're also building another gigafactory in Germany, which is right next to the Volkswagen plant. So that's a joint venture together with Volkswagen. It's these two gigafactories are probably not going to be the only ones that we're building, but these are the only two ones that I currently know of. And then we have a battery module assembly in Gdansk in Poland. So, I mean, given the fact that it's 2020 and we started with just like a handful of people, this is already quite an achievement. So what's our mission? In short, it's building billions of this. So these are battery cells. I think there are 2170 cells. And they so these battery cells are used then in multiple different applications. So you actually pack them then together into modules, and then they become assembled into subpacks and packs, so that you have larger battery blocks, which you can then use in large scale trucks or boats or as energy storage systems. In addition to the cylindrical cells that you see here, there are two other form factors which are frequently used. So the one is prismatic cells, which look more like Lego blocks, and then there are pouch cells, which are look more like a bag. So we're currently building cylindrical cells and prismatic cells, and they may end up in something like this, which is a block of energy storage. Which you can then assemble together and stack them and use them for voltage regulation or for temporary energy storage wherever this might be necessary. And this is one example where we're currently trying this. So we've built a battery in order to charge your electric car. So you're charging your battery from a battery. The more interesting example was was the first customer that we had, the first big customer that we had. This is Epiroc. So they're building underground mining equipment. So these are like 40-ton trucks that run deep underground in order to crush rock and carry it away. And these things normally run on diesel. And if you're in a mine, you need to spend a lot of money for ventilation in order to keep the air clean and breathable. So electrification is something that makes a lot of sense. So, but not all of our customers are like this, but this was the first customer. So we want to actually know how our batteries are doing, how our big batteries are doing. So we want to build some computers that we attach to these batteries and send us telemetry data. But these things are being rattled quite violently, and they're in environments where it's very warm and dusty and moist, and where there may not be good internet connection. Mines are usually not located right next to densely populated areas. So we had to figure out how to actually build a system that allows us to do software updates and collect data from the battery in offline environments for things that may be offline for months and that may only have like very, very sparse internet connectivity, and we still cannot brick the device. But we also didn't want to build something that is super, super special just for this one customer, because most of our customers probably won't have these requirements. And our Go software is currently running in these 40-ton trucks in the batteries that weigh about a ton and that are being used underground. So to give you an idea about where we're currently building these batteries, so this is a picture of the battery factory that we have in Västerås. So this is our test factory. It's about 20,000 square meters. It's 200,000 square feet. And it hosts a single production line. So the large building in the background, this is what we call upstream. It's where we mix the active material. So the way a battery is being produced is you have two components, anode and cathode, and the one has a graphite material and the other one has some active material, and you put this both on two foils, which are then being dried and pressed and cut and then wound up together and then put into a cell and then filled with electrolyte and a separator, and then charged, discharged, and that's then the cell. So the large building in front of this is are the two production lines for anode and cathode, and then the small building on the left is where we actually charge and discharge these batteries, and that takes about 3 weeks before the battery is finally done. So it takes about a day to build the battery, and then it takes about 3 weeks to actually form it and charge and discharge it. So this is a picture of the Gigafactory from summer last year. And in essence, we have the same layout. So we have the big building in the back, and then we have the longer building in the front. And right next to that, there's an area that's that leaves room for another of these long buildings. So we call these long buildings a block. And this one is like one upstream building with two blocks. And each block is a production line. But this one, each production line here has room for about 500 different machines of 70 different types. And it's clearly massive. And in order to give you an idea about the scale of these two different factories, so I have a picture here where you see a container, which is used as let's say as a reception. And then I tried to find another container somewhere here on that picture, and you see in the back. So I zoomed in a little bit and tried to find in the barracks there one of these containers for size. So this factory is about a kilometer by kilometer in size, and it will run thousands of our computers with our Go software. So what's the goal? In a very simple way, we want to collect all the data. We want to automate all the things in the factory, and we need to adapt or die. Batteries are still somewhat of a black art because it's quite difficult to predict how long they will actually last. So you can do this, but then you have to actually run them until they break. So which is not a great way of testing them, because if you want to find out whether a battery lasts 3 months, you actually have to test it for 3 months and then see, well, it broke after 3 months. So we would prefer if we can actually make some good predictions about the life of a battery. And we're trying to do that by understanding how we've actually built each individual cell. And not just in a general sense, that we actually collect the data for each individual cell that we've built. And since we're going to build billions of these, this is quite a challenge. The other thing is that the number of machines that we need to build, that we need to have in these production lines is quite significant, and they're going to be run 24/7 in 5 shifts. So we need a whole lot of people operating these machines. So we need to understand what they're doing, and how we train them, and how we can make things better. And the third thing is that I think with the focus on climate change and the decarbonization of our societies, I think it's quite obvious that battery development will get quite a significant focus in the next couple of years and decades. So there will be developments where we will just have to change, and we will have to be able to change quickly. So having factories is one thing, but being able to, in essence, just change them very quickly and learn from the experiments, this is something that normally isn't really done in production environments. So normally you set up a factory and then you use it. And then when you want to change it, then you tweak it. So if we dive a little bit deeper into the problem and just into the problem of from a software perspective, because Northvolt is primarily a manufacturing company, but we have a software department that is about 70 people. We're going to be more people next year. But we're never going to be a software company like Google or Amazon or Facebook. I mean, also not from hopefully from ethical standpoint, but we're just not going to be primarily a software company. So we have to figure out how production of batteries actually work, and then see how we can manage this, how we can actually collect the data from all these different machines. And to give you an idea about the scale, and it's not necessarily the scale of the data, so the amount of data that we're, that's our problem, but the complexity comes from the number of different machines that we have to interface with. So if we're just looking at a simplified step for the production process, where we have upstream, and then where we make the electrodes, and then where we actually assemble the cells in two different form factors, and then where we charge and discharge these batteries, we're looking at a total of at least 50, 60 different machine types. And then we have many, many more for automated vehicles, warehouse systems, clean rooms, building systems, and so forth. So when you're buying a machine for a factory, it's not like you buy a laptop. You don't go to the supplier and say, well, I want this one, and then they give you three. These are all custom built machines. They're built exclusively for according to your specification. Obviously, they don't start from scratch, but I don't think that any of these two machines are alike. Also, the data interfaces that we have there are all very, very very different. So the computers that we're dealing with are these two types of computers. So we've on the left-hand side, we have the PLCs, which are actually controlling the machines. So these are real-time computers. So PLC is for programmable logic controller. So they're microcontrollers. They're running in a main loop, and it's they're programmed in a very different way than typical time-sharing computers that we have with Linux and other operating systems where we're used to. On the right-hand side, we have like an industrial PC. So this one is it has an Intel CPU in it, an Intel Atom CPU, 4-core with I think 4 gigs of RAM. So this is where our software runs, and for each machine that we have that may have like one or more PLCs that actually control the machine, that do all the time critical and safety critical stuff, we have 2 gateways connected to this. So given for 500 machines for a production line, that means 1,000 gateways per production line. Since we have 4 production lines, that's 4,000 computers just in the factory in the north. So what this actually looks like is that for understanding how to get data out of these machines, these PLCs and these gateways are all mounted in DIN racks, and they're assembled way before these machines even hit the floor here in Sweden. So they're assembled at the supplier site and fully tested there, and then our people go there and then they make sure that when you press this button, this happens and the machine actually does what it's supposed to do. And then I package it up and put it on a ship and then send it here. So I think I just got permission to show one more slide. Let's see how I can do this here. Does it actually work? No, it doesn't work. Okay. So the way we do this right now is that we have to write a special application for every machine because they're all different. They all have different access protocols. They all have different data models. There is not really a common standard how the data of these machines is organized. So let's say 2 machines have a motor or a valve, and that may even be the same part, but the way you get the valve opening or the motor speed may be completely different. It may be different units, maybe different name. It's in different parts. You have to have a different access key. It may not be exposed at all. So right now we're writing special driver applications for each and every machine in order to translate this to a common data model. And of course, in order to make this somewhat doable, we maintain a common SDK among them. And we also need to maintain a common data model across the entire stack, because generating the data isn't the only thing. We also need to store it somewhere and make it accessible through APIs. Need to store it in some search engines. We need to store it for long-term storage. So schema evolution and schema management is a super important part for what we're trying to do. So in addition to this, we also need to be able to deliver reliable software updates, because if you have a factory floor that's a kilometer by kilometer in size, having 4,000 computers, not neatly stacked up in a data room where you can easily get to them, we need to make sure that we can deliver break-free updates for the operating system, for the applications, and which is similar to the problem that we also have with our connected batteries. In the factory, we don't really have to deal with limited connectivity, so we have fiber connections there. But the batteries also have to deal with long lifespans of products. So everything that we're using, so if we're uploading our data to some cloud provider, we need to be certain that this provider is going to be there in 10 or 20 years, because this is the lifespan of some of these products. So I'm wondering, with how many software services you've actually worked where you would surely bet on that they're going to be around in 10 or 20 years. So, how many smaller useful services would you use in such an environment? Or when would you decide, well, maybe we probably want to build this ourselves just to be on the safe side? So we then have to make sure that we can actually deploy this at scale, and so there is software to put Docker containers onto computers, but we don't really have the typical problem of bin packing. So it's not like squeeze as many containers as possible on the compute that we have. In the factory, we actually need to make sure that a specific container is run on a specific gateway, computer, and there may be different versions running there, because we actually do not have a dev environment. Because these machines are only useful when or only producing useful data when they're running and when they are producing. So not even when you turn them on is you get a lot of useful data. I mean, sometimes you can get some useful data. Let's say an oven is heating up, and that may take a couple of hours. But most of these machines only produce useful data when they're producing. And we can't put a multi-million-dollar machine just somewhere next to us to play with. And even if we had the money, we don't have the space for it. So we also don't really have the time and the people to write hundreds of simulators and maintain them, because the software development process in manufacturing is very different. So it's so a lot of times people just go there with laptops and plug that in with a USB stick or with a USB cable, and then upload the software to the PLC and then reboot. This is how software deployment works for PLCs. Because in general, you don't touch these things once they're done. But we're trying to change that. And that is create some friction, because the tools that we're dealing with are all very vendor specific, and they don't really support incremental change as well, because manufacturing isn't built for incremental changes. So the way they handle incremental changes is in essence give you a software and then give you like 200 parameters that you can tune, and then the person who's operating the machine knows the right combination of these parameters in order to make the machine do what we want. But for the number of people that we would need in order to, and the number of machines that we need to buy, this becomes quickly a problem of, well, how do we train these people efficiently, and how do we make sure they all have the same knowledge about the machines? So in essence, this is our problem. We need to build factories of factories fast. We need to understand how every machine behaves. Every process step has different machines, and they're all different. There are lots and lots of machines. These machines will run 24/7, and we cannot stop production. We have a bunch of different access protocols. So some of them are like binary ones, and that for which no Go library existed. So I had to write one. And we also need to know how every cell was actually produced, because we need a quality report for these cells. So if they cause some problems at a customer, we can actually know what kind of quality tests this specific cell has passed. And at the current time, my team has 3 people, including myself. One of my team members just went on maternity leave, but we were able to manage and write 50 applications and actually maintain them with just 3.5 people over the last 2 years. Because we were also making sure that we relentlessly focus on keeping things simple and making it easy for change. So in short, making batteries is hard. It's the hardest thing. It's the most complex thing that I've worked on in my entire career, and I'm still just scratching the surface. So to catch the corner, or to actually make the segue to go, I think if there is one thing that I've learned in working on distributed systems over the last decades, is that they're complex enough. So we should focus on keeping things simple. And the language actually helps us there a lot. So for one, Go is small and is fast. And by small, I mean it's easy to teach. It doesn't change. It has only 25 keywords, so you can super easily just teach it to someone, and they're probably grasp it in a very short amount of time. So what we need to look for are people who are able to solve problems with software. We don't necessarily need to look for Go developers per se, because it's really easy to teach them. It works on and cross compiles to a lot of platforms. So in the factory, we're currently running on Linux 64-bit. But we also have a couple of Raspberry Pis there. So we need to have Linux ARM7. Then there are a couple of edge cases where we're considering 64-bit Linux on ARM. We have macOS, and then we have a couple of tools that run on Windows 64-bit. Backoff PLCs, for example, support FreeBSD, which you can directly run on their industrial computers. So, and we can just say, well, FreeBSD is no problem because it's natively supported by Go. We just recompile our applications and they will just work. It's insanely beneficial that we really just have to recompile the application for that specific platform, and in general, we don't have to worry about anything else. The language and the standard library are incredibly stable, which means we never really have a whole lot of discussions about, hey, this new shiny thing came out. Shouldn't we use this? Shouldn't we use the new approach for talking to databases? And it means that we can really just focus on building applications and fixing them, because we will make a lot of mistakes. And all of these things in essence mean that, and this is what we've been doing for the last 2 years, is the next Go version comes, we just upgrade. So there are no questions asked. Every once in a while we check, I think for the latest time zone issue that we had from 1.15.2 to 1.15.3, we skip one, but in general, whenever the new version comes out, we just upgrade. GoFund means we don't have any discussion on code styles, and there's almost no dogmatic discussions in the team. And most of our code is just pure Go, so we can just compile and work on our applications and tweak them and tune them and refactor them so that we can make progress. So we have a handful of CGO applications that we need to do really high-speed image processing for line cameras that have like an insane amount of resolution that needs to be processed. And we're at this point, we're really pushing the edge about what's possible there. But even that is mostly possible with Go. The other thing is we have only source code. So for us, it doesn't really matter whether this is in a library, in our library, in someone else's library. The IDE just hides this for us and makes it accessible and makes it opaque. So we can just look at the source code and how the program underneath actually works. And then if we think, well, we need to fix it, then we can either fork it or have a patch. And Go modules make sharing code trivial for us. So, I mean, there is every once in a while discussion about, whether modules is really the right thing and, whether we should do this. for us, it's a real benefit, and especially if we have libraries or if we have packages that we can use in another project when we're not really sure on whether we want to pull this out into a separate repository, we can still share it because we can just refer to that specific version as long as there's a tag. It's easy, so it makes us super productive. All of these things, all of these little things, that they're platform independent, the compiler works fast, everything is source code, we can share the code, it all makes us very, very productive. So then we added a couple of things on in how we're using the language, and especially for that one project. So in general, we're following the approach that every project has its own repository, and then you have a CI system that builds it, and you have commits. But for the number of applications we have to maintain, we're actually putting everything into a monorepo where the SDK and the applications are all living in separate subdirectories, because it allows us to just drag everything forward. So we never have to maintain n different versions of the libraries. And because we're also pinning the Go and static check versions, we're also dragging the entire team forward with the next Go release, because we're kind of assuming that everybody is installing Go via Homebrew. Therefore, everybody has only one Go version. So if one project upgrades from Go 1.15.2 to Go 1.15.4, everybody has to follow, because otherwise the code will not compile. And that means the number of different version combinations we have to support is small. So we don't really have to look for a whole lot of different combinations. Finding the right patterns takes a lot of time, especially if you have to build that many applications. So making refactoring easy is super important for us. It took me a while to let go of seeing refactoring as something that, well, yes, we need to do this as it becoming really like a vital thing in our applications. But it's something that is just it allows us to move forward really fast and make changes to our applications and fix it. And then the fast compile times and the binaries and the platform independence help us to actually deploy this very quickly. So the other thing that we're seeing, at least in our applications, is that concurrency is everywhere. So we really learned to love channels. So instead of callbacks or locks, especially because we discovered the run group pattern from Peter Bergen a while ago, which in essence looks like this, where you just have in essence, you have a struct and you have a run function with a context and an error. So as long as your struct implements this, you can you can plug them all together, and they're all canceled the same way. And then you just plug the runners together and run them. So I think this is also similar to the R group that you find in the tools or extra package. But so this pattern allows us to have lots of different smaller components, which we can then compose and say, well, we need this and this and this, and then we do all of our runtime checking at the start of the run group. And then if the application startup fails, it just shuts down properly. And all the synchronization, and this is, I think, one, at least for us, it's an example where the channels really shine. And also the select statement really shines in making these enormously concurrent applications possible and understandable. So the last thing is that we started using code generation a lot. I think it's like 80% of the code that we have is generated, but it's mostly that we need data structures that are generated so that we can rely on the type safety of Go. And I think one of the learnings was that generating data structures is much better than generating code with the data structures, because then you can unit test the code and then just plug in the data structures. So what are the maybe one or two things that are not so great? So Go please is great, but it's still a bit unstable. That may also be just our use case, and I know that the team there is probably fighting. But every once in a while it just hangs, and then Visual Studio Code hangs, and but it's also usually pretty quickly resolved with just restarting the Go please server or reloading the window. So it's sometimes a bit annoying, but it's also not really a pain. And unfortunately, we also don't have time to debug this. We should, but right now we just don't. The other thing that I find a bit more annoying is that compiling seems to be a bit slower on macOS than on Linux. And that isn't really an issue if you have a small project. But our project has, I think, 400,000 lines of code. So it takes about, with the linter and code generation and everything else, takes about 12 to 13 seconds to build without any changes on the Mac. But if I run a virtual machine on the same machine with half the cores, it compiles in 8 seconds. And if you have to make lots of changes to the code base, to the entire code base, then this can be somewhat annoying. And we're still figuring out how to do error handling. So there was this huge discussion about, should we wrap errors? Should we have stack traces? The discussion that we had, I think, in the community 2 years ago or a year ago. So we're trying to figure out what actually is our best approach. Can we just live with standard error strings, or should we have error codes that we just define? So just one package where we define all the errors that we can have, or should we just do error types? And is there a way to, is there any benefit in using error types? But I think the one thing is quite clear for us, that error wrapping doesn't really provide any benefit for us. So we hardly ever look at the wrapped error or at the inner error. In general, if something fails, it fails, and we just bubble it up, because we have so little options for actually retrying or recovering from an error, and that it's just not worth it. So it's there, but we never use it. So I think the stack traces that we get from package errors are way more useful than the error wrapping. But it's just our experience. So then I mentioned that we also have these issues with the schema that we need to propagate. So all the types that we're generating. So if we want to say a valve opening, a motor speed, an oven temperature. So these are usually not just numbers, but we also need to provide some contextual information, and we need to define types for this. And what we found is that Go is a great language to just define types for other systems. So even if the Go types there aren't used directly, it's still great to use Go structs as the source of truth, because they're compilable. You can then write tooling to inspect them and then generate other type descriptions from this. So we have 2 examples for this. GraphQL, we're using GraphQL, and we started out with a project that was using schema first, using GraphQL types, but GraphQL has a type system that is somewhat limited. So it has only ints and floats, strings and bools. And sometimes that isn't enough if we have data that actually specifically says, no, this is a UN16, or this is an int16, or it's a float 32. So we need to know this type information somehow. And then GraphQL isn't really expressive enough to do this. On the other end, we have PLCs. They're using an access protocol that's called OPC-UA. So this is very Windows specific, or it comes from a Windows world. Floats are called reals, and or float 32s are called reals, and float 64s are called doubles. And the naming is different. So in order to, and there isn't really a good IDL and an interface description language in order to define these types. So we've decided to just use Go types as to define OPC-UA data models, and then generate the proper OPC-UA representation for that from Go, because we can. The Go tooling allows us to build great tools for this. And we all know what we need to do there. So to wrap this up a little bit, we're using Go in the factory, in the cloud, for connected batteries, for CLIs. We're running it on Raspberry Pis, on Intel, on GPU monsters with big NVIDIA cards in multiple 10 gigabit interfaces. We're using it on Linux, Mac, Windows, maybe FreeBSD. We're using it to collect data, manage our factory and batteries. We talk custom binary protocols. We collect and inspect images at high speed. We run APIs and deliver APIs. We ingest data through Lambda functions. We connect to databases and deliver software updates. So in short, Go is everywhere at Northvolt. So it's not just this little corner project or a small thing in the cloud where we're using Go. Go is everywhere, from the factory to the battery and everywhere in between. And I think there isn't well, I don't know if there are other companies who are doing it at that scale. I'd be interested to hear about that. So in addition to that, I'll give a brief overview of the rest of the tech stack that we have. So in order to keep the development environment simple, we're also keeping that the whole build and development process very simple. So in essence, it's Go, shell, make, and the monorepo, and boom, you're ready to develop 50 applications. We're using Go, Please, Static Check, and Visual Studio Code, mostly for sanity. If you want to use VI or Emacs, then that's also just fine. We're using Go shell and make to deliver 50 Docker containers with something like a custom build process, where we heavily relying on the reproducible binaries that Go delivers for cross compilation, because otherwise it would just take way too long to build these containers. Then for the rest, we're using Sentry for errors, AWS for scale, Grafana for dashboards, Terraform to bring the infra up and down, Elastic and Kibana for logs, and Prometheus and timescales for time series. So at the end, I want to show you a little bit about what it is that we're doing with all this data, because I'm pretty sure that I've explained a lot of the stuff that we're doing, and that is it's quite a number of things that we've done there. So let's get some pictures maybe. So the first thing is battery diagnostics. So one of the things that we're doing with the data that we're getting from the batteries that are in the mines and at some wind farms or at the charging stations is detailed statistics about all the cell voltages that we have per pack, per module, per subpack, usage, temperature, resistance statistics, so that customers can see how the packs are actually being used. It's a customizable user interface where people can click things together, and that's all then powered with a GraphQL API. This can actually go down to the actual cell group level. So we've in the beginning I've showed you the picture of all this big blue tray of cylindrical cells. And then you have cell groups, which are a couple of cells which are welded together. And so we can measure certain temperatures and certain parameters for an individual cell group, and then show this per module, per pack, per subpack. In addition to this, we're also allowing applications for battery maintenance, and then later also for factory maintenance, where in essence we know exactly where you are in the factory, and then and we show you error codes for the batteries if the battery management system has some errors, and we'll give you instructions on how to resolve them with that. And this also works online and offline. So it also works in the mine when you're in the phone with the phone in front of that machine. You can also look at that offline. Then the thing that we're doing in the factory is defect detection. So on the left hand side, so we're now looking at a strip of foil where the black part is coating. So this is either a graphite or it's the active material, depending on whether it's anode or cathode. And the colored spots are defects that our vision inspection system is catching. And then on the right-hand side, you see the gap between some properly coated material. So on the left-hand side, we have something that is not coated or not properly coated. And we can zoom in and zoom out and actually find all the different things there. So and the challenge with this is at some point, so we have a couple of kilometers of foil on a roll, but an individual electrode is only a couple of centimeters wide. So if we want to break this down to electrode level, we need to know which position of the foil we're actually looking at. But these foils cannot have markings on them because they actually affect the material. If we start to print onto the foil or if we start to make laser markings, they affect the active material on the foil. So how do we know exactly which part of the foil we took a picture of and which cell is this going to be once we cut it? We got maybe a small video from vision inspection where we're trying to do some live anomaly detection while the foil is running under the camera. And then last but not least, our operators who are running around in the factory, then doing everything with iPhones. So everything is marked with a QR code. Every cell has a QR code. Every foil has a QR code. Every roll where we actually put on the foil has a QR code. The machine itself has a QR code. The places where you put the foil on the machine has a QR code. And they all have special codes so that the operator can just scan these things and then the cloud knows what the operator is trying to do or is asking the operator, well, what do you want to do? Do you want to start this specific production order? And then the operator can say yes. And then the cloud will tell the gateway that is connected to the machine is okay, you can now start the machine. The operator actually loaded the correct material for this recipe into the machine, and then the machine will actually take over and will start. And that's and there is probably more, but I think I'm already running quite long. None of this would be possible without the tools that the Go community and the Go team have built. I mean, it is insane how far we could push this. This is way beyond I think the initial server applications where this started, and we're really grateful for being able to work with such great tools. And with this, questions.
Wow, thanks, Frank. That's amazing. Are there any questions for Frank at all? There's one here from Ivan saying, have you considered other languages for the task? What made you choose Go?
I mean, the main thing is that I wanted to use Go in the factory environment, but I was also prepared to say, well, okay, so if this doesn't work out, then we're going to use whatever makes more sense. And it turned out that Go is actually a really good choice for what we're trying to do, because it also means that we have to reinvent a couple of these things that are that weren't there before. So maybe if I rewind to when I started at eBay, so that was, I started looking at Go at the end of 2011, and then I started to introduce Go at eBay in my team in 2012, and I wanted to have one of the microservices to be in Go, but that wasn't possible because all of our config files were in properties files, and so I've started to write a library for that in order to make that happen. So and this then allowed me to write this was the final piece that was missing in order to build microservices in Go, and this is now it's like the properties library that's there. At Northvolt, it started out in a similar way. So OPC UA is a very common access protocol for Go, but there aren't really, or there weren't really any good libraries for this because this protocol is interesting. So, I mean, it's like gRPC with combined with TLS, but with its own TLS stack and without any of the tools that you have with gRCP. So I had to go to either say, well, no, we can't do OPC UA with Go because there are no libraries, or I had to write a library. So, and then it took me like 3 or 4 iterations until I actually had something that works. And so now we have, I was able to attract a couple of people who actually did all the hard crypto work. And so now we have an OPC UA library in pure Go. So the thing that's missing is a server component because the server is somewhat insane as well. But I'm sure if we need one, then I'll probably just going to do another push before I'll introduce the Python OPC UA server. So to answer the question, we're using Go mostly because they hired me. And I said I wanted to use Go, and I made it work. And the team made it work. So that's the reason.
Okay. There's another question here. Did you mention not having test environments? So what tooling do you use to catch errors before pushing stuff out to customers' batteries?
So all these so we don't have a test environment for the factory, but the tests are still run. So we're reporting, so the quality tests are run all the time, and we're delivering the data in order to compile the report. The challenge is that the challenge is how do we simulate, how do we have a what would the test environment actually look like, and what we're now doing is to say, well, okay, so we need to be able to detect when something is broken quite quickly. So we're leveraging Sentry for this because it will give us real-time overview if we have data quality issues. So let's say if a quality report is not coming in for a cell, but we're expecting it. And if one of our driver applications keeps crashing, then we can look at the logs and try to find out what's going on. And what Sentry makes it extremely useful is that we can augment it with contextual info. For example, the immediate link, which takes us directly to the logs. So speed for debugging the issue is a key thing here. Initially, I thought that we would need to generate hundreds of Grafana dashboards with alerts in order to maintain this, to be able to update 100 applications. But I think Sentry is probably a good compromise.
Okay. And another question here: do you use Go for the software on the batteries, which handles charging and discharging?
Yes. So we're also using Go. So I mean, we need to distinguish between safety critical parts and the the non-safety critical parts. So we're not using Go for the safety critical parts. So there is a battery management system which actually opens and closes the contactors. So we're not doing that with Go. So I think this is developed in C, and it's running on a microcontroller. So this is more traditional automotive way of developing software. And the same thing is also in the factory. The PLCs, they're also developed with the vendor-specific tools in their specific way. But everything in between then is mostly Go.
Mm-hmm. Okay. Another question in reference to the Mac performance issue you mentioned there is, have you looked at the directory cache performance on Mac OS?
So there is an open issue to this. I think something that changed between Go 11, Go 1.12 is that the Go team had to use a slower call for file system operation. So they had to go through the I think the C library on Mac, and we're also told by Apple to not make direct system calls anymore. And because that required them to make somewhat more expensive fsync calls, which in essence has the impact there. So there is a ticket open to which I commented, and if I find some time, I may do some debugging. But so far, we'll manage.
Another question here just is, Since the environment does not allow for incremental changes, how do you roll out software updates to batteries in production?
So we're not so the with the batteries it may that may then depend on customer requirements. So there we may have to agree with the customer when it's okay to actually upgrade, and they probably want to know exactly what changes went into this, because the battery is a product. The factory is a little bit different because there I'm anticipating that we will just we need to be able to make changes quick. So I want us to be able to, in essence, update the factory in a couple of minutes, everything in there. And I think we have the right technology to do this by just sending Docker Compose files to the gateways and have the gateways download their Docker containers from AWS. And since we generate all the Docker files, we can take big advantage of the layer cache. So in essence, we only have to download a couple of megabytes for every gateway. We start in a couple of seconds, we're done. I think the other thing that I really want to do, because I mean, people may remember Stuxnet, and Stuxnet happened because the Iran nuclear facilities in Iran got compromised, or the Siemens PLCs there got compromised. So we're also putting the gateways in front of the PLCs in order to protect them a little bit. And that means that we also have to deliver software updates there. And I expect that at some point we may have a breach. So I want to be able to wipe the entire factory and press the reset button, then everything gets reflashed, rewritten, all the gateways install latest version of the software, and then download the containers, and off we go.
Cool. One more question here. Did you get any pushback on choosing Go?
So initially, I was the team. So that in there well, I mean, there was one other guy I was also working there, and sure, there was a little bit of pushback. But I think in general, it's the company has embraced that, and they're also seeing the benefits of it. There isn't really a big discussion on whether this was the right choice, but I would have also been very prepared, and that was that at eBay as well, that if there would have been significant pushback and from the team, and good arguments on why this doesn't work, then sure, we would have dumped it. The point is that I think that the Go team has made very good decisions on what to include in the language and how to steer this over the last years, over the last decade, to keep it really stable. That this is a significant advantage. So I remember the times when we were going from Java 4 to 5 to 6 to 7, and then every time you had to figure out whether something significant had changed. And with Go, we never have to do this.
Cool. And someone's asked, do you have any difficulties in hiring engineers knowing Go? As you mentioned before, I think you think it's the easy part is teaching them Go, right? So
we have so my experience is that I'm able to hire a good engineer every 2 months. So that's and this is when I'm doing nothing but interviewing. So I think right now we're still on that pace. We may get lucky right now and may have a bunch of candidates coming through, but in general, I don't care whether you know Go or not. I care on whether you know how to break larger problems down into smaller pieces and know how to solve problems with software, because teaching Go is easy. The team at eBay I had there, I've in essence told them, okay, here tour Golang org, go learn it. And then they learned the language more or less in a week. And then let's say it takes another 2 weeks in order to get a hang of the concurrency issues. But it's more about finding the patterns and then understanding that a lot of the tools that you had used before, you no longer need. And then it becomes really liberating. And then you also see that you just need engineers and not necessarily engineers knowing Go.
Cool. That was amazing, Frank. Thank you very much. I think we've gone through all our questions. It's a really interesting talk, and it's amazing to see the applications of Go at such scale as well. Fantastic. Thank you very much. And as you see there, you mentioned your Northvolt is hiring. So if anyone's interested in what they just heard, get in touch with Frank.
Yeah.
I think is the message there. Definitely. Thank you very much, Frank.
Thank you very much for having me.
Anytime. Come back again.
Sure.
Great. Well, just to round off the evening, and so we have a winner for our JetBrains license, which was Cyril Hemedy. So well done, Cyril. I think Alan will get in touch with you with the details of how to pick up your license. In terms of our next meetup, so we've got one lined up now for the 17th of December, which will be another great evening, we think. We've got Bill Kennedy's going to speak to the group, and he's going to be talking about the generics draft proposal. So that should be an interesting talk as well. Bill's always a great person to listen to speak, lots of energy, and it's always got someone interesting to say, I think. So definitely make sure you sign up for that one and tell your friends to come along as well. The more the merrier. And that is it. So once again, big thanks to Daniel and Frank for their talks this evening. That was really, really interesting evening. Thank you very much. Thanks again to all the sponsors, and thank you all everyone for attending. And yeah, I think last time we kept this open a little bit so people could have a little chat if they wanted to afterwards, in lieu of having a beer or a pizza. But until next time, we will see you then. Thank you very much. Good night.